Okay, last but not least, phase diagrams. Phase diagrams are a way of just mapping out and showing the relationship between the phases or states of a substance as a function of pressure. The regions on your phase diagram will represent where you have solids, liquids, and gases, and the lines will tell you at the temperatures and pressures at which there's an equilibrium between the two states. Okay, triple point, that's a special condition. All three states are equally stable and in equilibrium. It's a little different, like if I just put a piece of ice out on the table, that's not at equilibrium. If I let it sit, the ice is going to melt. At triple point, under that pressure and under that temperature, I put a piece of ice out, it will stay as the piece of ice. I put some liquid out, it stays at the liquid. The amount of ice and the amount of liquid can interchange, but that will always stay constant. The critical point, we mentioned the definition for that. I'm going to show you on your phase diagram. That's at the temperature and pressure where you no longer can distinguish between your liquid and your gas states. It becomes what we call a supercritical fluid. Okay, so let's talk about the phase diagram of water. Okay, it's not to scale, as you can see. On my x-axis is my temperature. On the y-axis is my pressure. In this case, we're using my pressure in atmospheres as my units. So when we look at this line up here, and you have a line here, this segment here, this is the solid, this is a gas. So going back and forth here, it's sublimation this way, deposition that way. This is the equilibrium line between a solid and a gas. Okay, as I continue to increase my pressure, what we find is that at higher pressures, I can go from a solid ice to a liquid, water, and water back to the ice. So at 1 atmosphere, okay, my equilibrium between solid and liquid is going to be at 0 degrees Celsius. And notice there is a small change, but not a dramatic change in terms of my equilibrium. So as my pressure decreases, I can be at slightly higher temperatures to be at equilibrium between ice and water. Here, this section, I'm going between liquid and gas. So this is vaporization, this is condensation. This one is melting, this one's freezing. This one, sublimation, going back, is deposition. So, it's showing all the equilibrium. Okay, these lines represent where you have your equilibrium between your two states. At 1 atmosphere, going between solid and liquid, freezing point, 0 degrees Celsius. If I look at 1 atmosphere, going between liquid and gas, this point right here is my normal boiling point, 100 degrees Celsius. Now, if I continue to increase my temperature and I continue to increase my pressure at 374 degrees Celsius and 225 atmospheres, critical temperature, critical pressure. This is called the critical point. In this section up here, water, or H2O is actually not water. H2O is a supercritical fluid. You can't distinguish between the gas phase and the liquid phase. So if I said, using this graph, tell me, what do you think if I have assuming this is like 0 to 100, so let's go halfway here. If I have a 50-degree temperature, at what pressure would I be? Would that be my boiling point? So at 50 degrees, you go up. You say, oh, listen, this is, let's say, well, I know it's not a scale. Let's just say it's halfway there. So at half an atmosphere is where you would get from this graph, basically 50 degrees from my boiling point. Okay, so you can read the graph just like we've been talking about earlier, as long as it's to scale. But now you know the different sections of it. That's the important part. is to be able to interpret these phase diagrams. This is also another pressure temperature phase diagram. It's for carbon dioxide. And what we find is this. If you look at 1 atmosphere, carbon dioxide will go directly from a solid to a gas. And that occurs at minus 78.5 degrees Celsius. So basically, this is sublimation. You have to get to higher pressures before you see carbon dioxide occurring as a liquid. So at 5.1 atmospheres, that's where I can get carbon dioxide existing in equilibrium as a solid, liquid, and a gas at minus 56.7 degrees Celsius. If I continue to increase the pressure, you can see there's not a lot of change in my temperature before I start going from solid to liquid and then liquid to gas. Okay, but we're at much higher temperatures to work with. And like I say, if this is my critical point, this is my supercritical fluid. Okay, not a high temperature, that's only 31 degrees Celsius, but look at my pressure, 72.9 degrees. And over here, we can't distinguish between carbon dioxide as a gas or a liquid. Okay, so here's a phase diagram for ammonia. Just so you know, this is in bars. And for bars, basically 1.01 bar is equal to 1 atmosphere. So basically, just around here, look at, that's my triple point already. All right, so we're talking about some significant pressures. But here's the thing that's more interesting. Okay, if you look at ammonia phase diagram, going from solid ammonia to the liquid phase is pretty much at minus 75 degrees Celsius. And that equilibrium doesn't really change too much, right? If you look, that temperature minus 75 stays pretty constant regardless of my pressure. Okay? If I look at 1 atmosphere, okay, which is about 1 bar, which is very close to that 0 line right here, you can see that the equilibrium between my liquid phase and my gas phase is right around here. Okay, so basically what we're saying is that if this is my triple point, that's my liquid phase, we're at, let's say room temperature is 25 degrees Celsius, 1 atmosphere, we're right here. Okay, the bottom line, that's why when we talk about ammonia, we're primarily talking about it being in the gas phase, because we're right here when we talk about ammonia. If we wanted liquid ammonia, okay, either we have to be really cold, and if we do that, we're talking about minus 78 degrees or colder, okay, because we want to get down to this phase right here at 1 atmosphere. Or if I wanted to get to liquid phase, I can increase the pressure. So here's 25 degrees. I can increase the pressure so it's greater than 10 atmospheres. Then we can start getting ammonia occurring as a liquid. Okay, so for our considerations, because we're right here, we can see that we're going to be pretty much in the gas phase for ammonia. So this is my critical point. Up here is my supercritical phase. That's my supercritical fluid. So I said, oh, okay, so what phase would ammonia be at 60 bar and 0 degrees Celsius? So here's my 0 degrees Celsius. Let's go up to 60 bars. And you say, oh, it's going to be in the liquid phase. If I said, well, I wanted ammonia as a solid phase at 40 bar, then you'd go and say, here's 40 bar. Liquid gas phase, no. Liquid phase, no. So to get to the solid phase of ammonia, you'd have to be less than the minus 75 degrees Celsius. So that's how you can use this graph. Actually, less than minus 77.65 degrees Celsius. So that's how you use a phase diagram to interpret how your substances are behaving. So be aware of the different parts on a phase diagram so you can interpret phase diagrams.